Okay, so let's continue. This week we are going to talk about the range of a matrix and the rank of a matrix, of matrices. Now, these two statements, these are two parameters or measurables for a matrix. One of them, the range, it has to do with columns, okay? And the other one, it has to do with rows. So the matrix, if we, in one of them, we are going to consider what is going on with the rows, and with the other one, we're going to see what is going on with the columns. Now, we have seen these not the same concept. We have not defined this before, that we have the range or the rank, but we have seen these principles when we have done the solution of systems of linear equations. So that much information, you already have it, and we remember the following, that whenever we try to solve an equation which looks like this, AX is equal to B for any for any system that looks like this, we know that the first step is we try to obtain reduced row echelon form of A. Okay, so reduced row echelon form of A, it is the simplified version or the sparse matrix representation of the initial coefficient matrix. So this reduced row echelon form here, if we look for the number of leading ones, okay. If we look for the number of leading ones, this defines the rank of a matrix. When we say the number of leading ones, we can also call this one the number of non-zero rows. Okay, so we look at the rows, and if we have any row which figures out to be full of zeros, then we subtract one from the number of rows of a matrix. So presumably, let's assume we have a matrix which is, which is 3 by 4, okay? If we have a coefficient matrix which is 3 by 4, what could be the vector which multiplies this matrix A? What is the dimension of this vector X? Someone can answer this?
4 by 1.
Okay. Now this would be equal to what? This is B. What is the dimension of B?
3 by 1.
3 by 1. Okay, that's true. So this is how, and this is how this is how the dimensions of these parameters change. And now that we mentioned here the columns, you might take a note right away that the range, which is related to the columns, maybe it has to do something with B 3 by 1. Okay, so, and we care about this one because we often try to determine what is the domain of B. For example, B is a subset of what? If we look here, B is it's a subset of R3. Sorry, let me do this again. Of R3. Why? Because it's 3 by 1. That means that we need a triplet of numbers to determine what is the B. Now, let's see an example here. As an example, let's pick up a matrix which is 3 by 4, and it goes like 1, 2, 1, 1, 2, 3, 0, 5, and 3, 5, 1, 4. So here we have a matrix, and we want to determine what is the rank of this matrix. What is the, so you go to a test, and you are asked, find the rank. What should we do? We should obtain, we can do the following, get or obtain reduced row echelon form. So this is the question. How do we do that? We try to obtain leading ones. So let's put here we have a leading one. How can we zero out these elements here? We can write here row 2 star can be written row 2 minus 2 row 1. Okay, the first row does not change, 1, 2, 1, 1, and then here we have 2 minus 2, 0, 3 minus 4 is minus 1, 0 minus 2, minus 2, 4 minus 2, 3. Then we got this one. Now we need to make a 0, this 3, and for this we can write 3 star, row 3 star is equal to row 3 minus 3 row 1. So in this case we have here 0, and then we have 5 minus 6 minus 1, 1 minus 3 minus 2, and 4 minus 3 we get 1. Now, this is the next step. The next step is that we want leading ones, okay? So we want number ones at the beginning of each row. Let's make this a leading one. How can we do that? We can say that row 2 star, this can be written as minus 1 times row 2, okay? And if you allow me, I can do the change right here. So we can do this one minus 2 plus 2 minus 3. Now here we have another leading one, we are good. The next task is to obtain a 0 below the 2, 2 element. Because we want to make zeros this here, or we can say that also we want to make zeros here. And of course, reduced row echelon form, this includes also making some zeros here, and making some zeros also here. So this is what we should be doing. Now, how can we make this 0, row 3? We can say here, I think you can see this part of the board, we have here row 3 star would be equal to row 3, then what? What should we write?
Plus row
2.
That's true, plus row 2. So we just add those two together because 1 minus 1 is equal to 0. So let's write this here, 1, 2, 1, 1, 0, 1, 2 minus 3, 0, 0, 0, what is this? Minus 2. Okay, we can improve this a little further. So we have leading one here, leading one here. How can we make a leading one here at minus 2? We can say row 3 star, this is equal to row 3 divided by minus 2, right? So if we do this, if you allow me, I can do this, the change right here. So we can put here a 1 plus 1. So then the reduced form is here. Now the question is that, is this the reduced row echelon form? What is this? Is this reduced row echelon form?
No, it's just row echelon form.
That's true. No, this is just row echelon form. Why? Reduced row echelon form would be 1. So what should we have now? Now we should have the following. Wherever we have the leading ones, so leading ones are around here, we should make zeros where the leading ones are. Okay, so we are left with these and these. We should do this. So once we get done with this, then that would be the reduced row echelon form. So this is not yet there, but we can conclude something at this stage, at this point, by counting the leading ones. If we have 3 leading ones here, that means that the number of non-zero rows is equal to 3. So at this stage, we can say that the rank of this matrix A, the rank of matrix A is equal to 3. Okay. So this is how we report the rank of a matrix. Now, so this is how I think this is clear. Now it's time for us to provide a theorem, and a theorem which should be very useful to us, which states the following. Main theorem, it states that if we have A, which is an n by n matrix, how do you read that statement on the board? Apparently, we have a matrix which is square matrix, which is n by n. We are not talking about a matrix which is n by n, like in here, okay? But let this be square. Then the following statements are equivalent. So the following statements are equivalent. What are these statements? The first one is A inverse exists. The second statement, so let's assume that if a matrix is a square matrix and A inverse exists, then AX is equal to B has, does this system have a solution? What do you think? So if A inverse exists, does
It has a unique solution. It has a unique solution.
Why does it have a unique solution? You're right, that's correct. Let's try to understand why this is a unique solution. What we can do is that we can multiply this equation from the both sides with A inverse. Let's do it like this. A inverse times something. This is equal to A inverse times something else. Now here we do AX, right? Here we have B. What is A times A? A inverse times A. What is this?
The identity matrix.
Identity matrix, and this here we get that X is equal to, so AX is equal to A inverse times B. So this means that this is pretty well defined for this reason. You are right. We can erase this one. We just try to clarify this. So AX is equal to B is consistent. What do we call consistent? A system that has a solution, at least a solution. So this has a unique solution. For any B, B can be any number, okay? The third statement is that AX is equal to 0. What could be the solution for AX equal to 0?
Trivial solution.
Yes, and the reason is that AX is equal to 0, it has also a unique solution, but only one solution. But this single solution is a trivial one. Okay, so it's still only one, but we say that this has only the trivial solution, and the trivial solution is the vector 0. This is the solution. Okay. The fourth statement, which is equivalent to the first three, is that reduced row echelon form of A is what?
Identity matrix.
That's true, this identity matrix. So that's what we have here. And then the determinant of A, any guess what can we say about the determinant of A?
It's not equal to 0, maybe.
That's true. It's different from 0.
Because if it's equal to 0, then the inverse cannot exist.
That's exactly true. So these two are closer to each other as concepts. So this implies this immediately. And the last statement is the following. The rank of A is equal to n. Okay? So the rank of a matrix which has an inverse is n. Then this is the statement. Let's see an example here. Let's assume we have x1 plus 2x2 plus x3. This is equal to 1. 2x1 plus 3x2. This is equal to 5. 3x1 plus 5x2 plus x3, this is equal to 4. Okay, so here we have a system, and let's try to see, let's analyze what could be the rank of A and the rank of AB. So we have a system of linear equations, and whenever we try to solve it, we know that we have a construct, which is the matrix A, and we have another construct, which is the merging of the A and the B. What do we call this, the merging of A and B?
An augmented matrix.
Yes, that's true. We get the augmented matrix. And now, both of these two matrices, they have a rank, right? Let's see what is the rank of A and what is the rank of AB. What is matrix A? This is 3 by 3, right? AB is what? It is 3 by 4. So let's write this, the augmented matrix. We have here 1, 2, 1, 1, 2, 3, 0, 5, and we have 3, 5, 1, 4. Okay, so let's follow the same steps. We want to get the reduced row echelon form to obtain the rank. What do we do? Row 2 star. Okay, we subtract twice the first row. Would you agree with this one? So we say row 2 minus 2 row 1 and row 3 minus 3 row 1. So then we get the following 1, 2, 1, 1, 0 minus 1 minus 2, 3. We get 0 minus 6 minus 1. What is this? Minus 3 times? Wait, no. Minus 1, 1 minus 3, minus 2, and we have 4 minus 3, we get 1. Okay? Then, what is the next step? We can try to make leading 1, because we have a leading 1 here. How can we do this leading 1? We can say row 2 times minus 1. Okay? And this becomes like this. What is the next step? This is the other leading 1. Next step, we can say row 3 plus row 2. So if we add these two together, we're getting the following 1, 2, 1, 1, 0, 1, 2, minus 3. And what do we get here? Okay, so this is what we obtain. Now, we can still get a leading 1 here. How can we do that? We can divide by minus 2, and we get here 1. So, what can you say about this system? What is the solution of this system?
There is no solution.
There is no solution.
Because of the third row, we have 0 equals to 1, which is impossible.
That's true. How do you read the third equation? The third equation, it is 0x1 plus 0x2 plus 0x3. This is equal to 1. This has no solution. So it looks like we have no solution when? Rank of A, what is the rank of A if you see the matrix here? What is the rank of A? Can you see it from here?
2.
2.
It's 2, that's true. And the rank of AB, what is the rank of AB?
3.
3. Now, if the rank of A is not equal to the rank of AB, or let's say it like this, rank of A smaller than the rank of AB, then what can we say? We could say this statement, okay, no solution. Why? Because we would have zeros could be equal to some non-zero value, which is impossible. So apparently, it looks like this is one use of the rank of the matrix. It can help us to determine whether the matrix, the system of linear equation, is consistent or not. Now let's try to change this matrix a little bit, and let's make this 4. Let's make this 6. Okay, and to make this 6. We'll get the following, we get 1, 2, actually I need to use this part, so let me delete this. So we have 1, 2, 1, 1, and we have 2, 3, 0, 5, 2, 3, 0, 5, and 3, 5, 1, 4, 3, 5, 1, 6. Okay, let's make it 6. We have everything is the same. We just change this 4 into 6. And actually, I deleted the equations. I wish I had kept them. So what was the first operation that we did in order to make this 0? We said it was row 2 minus 2 row 1, which would mean that here we would have 5 minus 2, this would be equal to 3, right? And here 6 minus 3, this would be another 3. And after the very first step, actually I just applied I applied these changes right away here to see how this vector is changing, because the rest of the steps would be the same. So after we get this, we would be in this state, would be somewhere here. But wait a second, this would be 5. Okay, yeah. Actually, let's do all the steps, maybe that's better. 5, 6, okay, let me do this, 5, 6. Okay, most probably you can do this faster than me. We subtract 2 minus 2, 0, 3, this is minus 1, 0 minus 2, minus 2, 5 minus 2, this is equal to 3, then we have 0, minus 1, minus 2, and 3. So this is what we can get right away. So what do we observe here? We observe that the second row is the same with the third row. What does this mean? This means that we have two equations which say the first thing, which means that one of these is redundant, it is useless. So, and even if we don't consider it useless, we can always write that row 3 star would be equal to row 3 minus row 2. If we do that, here we get all zeros. Would you agree with this? So this is the new configuration with a single change of the B vector. Now, let me think also the following. Can you check what is the determinant of A? Can you find the determinant of this matrix here? The 3 by 3? Or let's continue, and we can think about the following. Does this system have any solution? This system here? And by the way, wait, let me think. What we can say is that as we are doing elementary row operation on a matrix, the determinant is not going to change. Okay. In fact, the only change that happens on determinant is when we exchange row y with row j. Okay. If we do such an operation, the determinant is multiplied by -1. Other than that, the determinant will not change. So I can ask you the following. What is the determinant of the coefficient matrix A? And that information, you can also obtain it from here, from this 3 by 3 matrix. What is the determinant of this 3 by 3 matrix here? What can you say about this? I'm going to pick someone, Ermali. Ermali, what is the determinant here? The determinant of this matrix, which I'm circling in red. Ermali?
I think we should do the calculations first.
Grievous, raise your voice.
I think we should do the calculations first.
I think too. I would agree. So let's go ahead with it. I mean, can you do it? I think we have to do the calculations. Yes, that's what you signed up for when you selected electronics engineering here with us.
Okay,
So,
if we take the first row,
yes,
number 1,
times,
1, 2, 0, 0.
okay,
And then if we take number 2, it's 0, 2, 0, 0.
yes,
And then it's 0, 1, 0, 0.
yes.
Then it's 2, 1,
Is
0,
the
0.
determinant here?
Oh, the determinant. It's 0.
It's 0. That's good. Well, there's nothing, but it's 0. What about here?
It's 0, 2. And in the other it's 0.
So we have 1 times 0 minus 2 times 0 plus 0. This is 0. So it looks at the determinant here is 0. And if this is 0, the determinant here also is 0. So the determinant of coefficient matrix A is 0. So we can add information here by saying the following. If the determinant of a matrix A is different from 0, what do we have? We have one solution, unique solution. Okay? If the determinant of a matrix A is 0, like in this case, we can have an infinite number of solutions. Okay? And also, we can have no solution. Let's try the 0 solution. So, this is what we have here, but this is what we have here. So, this is consistent, and this is inconsistent. Inconsistent. So, let me see, I think we can do it like this. So determinant different from 0, it is consistent. One solution, determinant equal to 0. We can have infinite number of solutions, which makes it consistent. Or we can have this other option. So it looks like if the determinant is equal to 0, we cannot answer right away whether we have a solution or not. When the determinant of A is equal to 0, we have to look for this vector here, B. So it looks like it greatly depends on how B is changing. Now, if we want to provide a solution, I think at this point, in less than a minute, we can provide the answer, which would be the following. Actually, we can improve this a little more by making another 0 here, and we can do that. How can we make this 2 equal to 0? Row 1 minus 2 row, sorry, row 1 minus 2 row 2. We can change it. This becomes 1, 0, minus 3, 1, plus 6, 7, and this is 0, 1, 2, minus 3. So this is all the information that we have, and the leading ones, they are here. Which one is a free variable? X3 is a free variable, okay? So if X3 is a free variable, we can write it like X3 is equal to S. And then we have the following equations. We have X1 minus 3S, this is equal to 7. And X2 plus 2S, this is equal to minus 3. And finally, we can write down here that X1, X2, and X3, this is equal to any constant vector plus S times. So what is X1? We get here 7, 3, 0, 1, minus 2, 3. So what is the solution? What does this expression give? Let me ask Ermal again. Ermal, what does this solution provide? What is this?
Sorry, can you say that again? Because
Yes, Ermal, what is this equation that you see here? This solution?
it's a matrix.
No, this is the equation that looks like this: P plus S times V. What do we call this? Come on, everybody. I mean, you should. Everybody. It's a line, maybe.
It's a linear equation.
Yes, but this is the equation of a line. So this is the equation of a line, okay? And what is the dimension of a line? Let me ask the next, Esther Berdufi. What is the dimension of a line? Esther? After Esther, we have, yes, Esther?
It is one-dimensional?
Exactly, okay, that's how we write this one. So this is one-dimensional unit or structure, one-dimensional structure. And let's try to analyze, Esther, this carefully. We had the matrix A, which was 3 by 3, right? What is the number of unknowns? Sa pa një ora ka kjo ekuacione këtu lart. Let's not forget, we're still working on the same exercise, the same example. Only the...
Professor,
Yes.
sorry to interrupt. I wanted to ask you something. You said that the line is in one dimension, but there are, if I'm not mistaken, there are 3 variables, like in the column vectors down there. So does that mean it's a line in the R3 plane, in the R3 space, or?
Yes.
But what does this one dimension define that you wrote there? Is it just for the line, not for the space in which the line is at, or how would you describe it?
Yeah, this is a good question. So let's think about the following. The 3-dimensional space, let's consider the Euclidean, the Cartesian coordinate system. It has x, y, z, which are 90 degrees with respect to each other, so they are orthogonal, okay? And this is a direction, 3 minus 2, 1. What would be this 3 minus 2, 1? Assume that I'm standing here, okay? And the x-axis, it is extended, or let's use this part of the board, okay? Let's try to use this part of the board. So I have a line, let me draw it right here. So let this be one line, which extends like this, okay? How are we going to call this one? Let's call this one x-axis, okay? This line, this is the x-axis. Then you can draw another line which is pointing to the camera, to you, okay? So I can think about this one. This is an orthogonal. This is the y-axis. Where is the z-axis? We can take the cross product of x-axis using the right-hand rule, and you are electronics engineering, you're going to use right-hand rule in electromagnetism a lot, and in the field theory, so you better understand it now. So the x-axis is pointing in this direction, you rotate your fingers toward the y, and this gets the z-axis, so this is z. Then what is this 3 minus 2, 1? 3 minus 2, 1, it is 2 units along the x, 3 units along the x, 1, 2, 3. We get 2 units into the board, okay? So imagine now a vector that is going through the board, okay? That makes it minus 2 units, and 1 unit along the z. So you can imagine a direction which is going to point, like here, at this point, you go deeper by 2 units, so it's going to be a vector which is going to point, if you look from the top, it's going to look like this, okay? It's going to point somewhere in this direction, okay? But that's a single line, that's true. In 3-dimensional space, you need a direction. but it's just a line. And this line, you can do it like this. This is the vector, okay? And then you multiply this vector by 1, you get this point, right? You multiply this vector by 2, you get this. You multiply this by 3, you get this. You multiply by 0.5, this. You multiply by -1, you get this. By -2. So it looks like we can construct a line. So that's what this gives, okay? This is the equation of the line, this one here. But if you join all of these points, this is a line which is two-dimensional, okay? Is it clear now?
It's so you're saying it's two-dimensional?
No, you said it. I cannot say that.
Oh, okay. I did not hear it well. Maybe. So you said it's one-dimensional.
It's one.
Okay, sorry, because the connection isn't very good today. That's why.
No. But thank you for the question. That's good. So this is one-dimensional, and now we were talking with I forgot, with Esther, I think, or who was?
Professor, so just to conclude, you say that the line is one-dimensional because it spans in one dimension, like it can expand by a scalar in one dimension.
Yes, because it can draw. So let me say it this way. Wait, let me think. Yes, you can say that exactly. So a single vector, all it can do, it can span one dimension. What is the next best thing that the line can do? Well, can you span a plane? Can you describe all the points in a plane using a single vector? Because if it cannot do, let's say, the first option is to span one-dimensional space. Fine. What would be the next best thing? It would be 2D. Can it do the 2D, two-dimension? No. So all it can do is just, you can describe all the points in one line. So this is this 1D. The plane, the plane is two-dimensional, okay? Now, if you get out of the plane, you get 3D, you fill up a volume. So, with a single vector, you fill up a line. With two vectors, like this and this, you can describe any point on this plane, okay, with two vectors. With three vectors, you can fill up the whole room, because you have x, y, z, so any point in your room, you can describe it by elementary directions, x, y, and z. Is it clear?
Yes, thank you, Professor.
Thanks. And let's discuss again with Esther. So Esther, please, how many unknowns does this system have?
3.
3 unknowns, okay. 3 unknowns. Okay, how many equations do we have?
3 equations.
Actually, we start with 3, but we don't really have 3, right? We have 2, because one of them is linearly dependent with the first 2. So we added 3, but it's not because one of them is dependent with the others. We end up having 2 equations. If we have 2 equations, what does this mean? Having 2 equations, that means that we have 2 leading ones, or we can say that the rank is 2, right? So we have 3 unknowns. When we say we have 3 unknowns, we said n is equal to 3. Okay? What is the rank? Rank is equal to 2. Now, the number of unknowns minus the rank, this gives us a number, which is the number of free variables. Okay? So you can take this as a node that we learned them from the number of unknowns minus the rank. This would be the number of free variables. And in fact, this would be then the dimension of the solution. Solution space. Let's call it this way. So this system, it had an infinite number of solutions, and then and all of these infinite number of solutions, they all describe a single line, and this line is one-dimensional, also for the reason that when you subtract these, this is what we get. Is it clear?
So, Professor, to
Yes.
sum up, we need to make a row full of zeros?
If it is possible, yes.
And
You
then
don't have
we have to make the calculations to find the values, or
uh,
because I think it's a PI. I'm confused right now.
okay,
Yeah.
so we try to produce as many zeros as possible, and how can we do it? We try to identify the leading ones, and we make zero. So if you have one leading one, for example, the moment we observe that this is a leading one, okay, that this is a leading one, our task is to produce zeros here, because we can do it, right? And then our task, because using this, atë numra që e nisha në Echelon, dhe nëse leading numbers, leading ones, ato do të bëjnë zero gjithë të tjera, do të rinë vetëm te kolona e tyre. Në rregull?
Profesor, po te kolona 1, 2, 0, po.
In here.
Jo, te tjetra. Do të thënë 1, 2, 0, 1, 2, 0. 1, 2, 0, 1, 2, 0.
Where? Here or here?
Ana profesor më shtu. Vum fare po, kështu në solution, është kolona si për 1, 2, 0. Dhe se kemi prek fare për shkak.
Ku është 1, 2, 0? Oh, here.
Ai, që bëm 1, 2, 0. Ai e vi.
But this one, yes, that's true. We did well. Let me think. No, this is simplified because we have a leading one here, we have a leading one here, and we make a zero. Okay. So the issue is that we try to make as much zeros as possible, which in another way, this means that we determine where the leading ones are, and we leave these leading ones alone in their columns by making all the rest zeros.
Profesor, pa nuk kemi mësuar për shembull që tek row 3 të marrim leading one të tretën, që ta bëjmë nish të si bjerë, R3-shin ta bëjmë nish, pastaj të vazhdojmë.
But apparently it's not possible because it looks like, I mean, it's not that you want to do that, but when we're doing the equations, it ended up being zero. Okay, so I mean, this is what we get.
Ok, profesor, se do me thënë kolonën 3, 1, 2, 0, se kemi prek fare do. Ne kemi mësuar që 1, 2, 0-ja, 0 në fund ta bëjmë leading one.
You mean this one?
Fix.
Okay, but this one, we did not simplify this any further because we found out that there is no solution. But this one, we cannot change this. It is impossible for us to change because we don't have a leading one here. The leading one, they are here, here, and here. It is true, we can make zero, the 1 and the -3, or these two, yes. We can do it, we can do a couple of more steps, but so this is something we cannot change it at all, this one. It will be modified, why? Because when you do the operations to make this zero, this will change, okay? Actually, like, where did we do it? If you want, we can solve this one a little further. So let's try to clarify the doubts by doing, so what operation can we do here? We can make, well, we can make this -3, we can make it 0, right? How can we do it? We say row 2 plus what?
Plus 3 rows.
Plus 3 row 3, okay? Plus 3 row 3, that's good. How can we make this one 0? Finishing to row 1 minus row 3. Okay? So then, let's continue. What is row 3? It is 0, 0, 0, 1. And then we have here, this is 0, 1, 2, 0. And then we have row 1 minus row 3. This is 1, 2, 1, 0. Okay? We did this. Then what is the next thing we can do? Let's notice where are the leading ones. Again, the leading ones are here, which we can denote them also by drawing such a line. The next step is to make this 2, 0. Okay? Now, how can I make, do you want me to continue this one? How to make this 2, 0?
No, it's understandable.
It's understandable. I could use this one just for to keep all in one place. It's true. This is both understandable and intuitive. But we have 0, 0, 0, 1. And then how can we make this 2, 0? This would be row 1 minus 2, row 2. Okay? Row 1 minus 2, row 2. So we have, this is 1, 0, 1 minus 4 minus 3. And then we have, what is the rest? This is 0, and this is not going to change. 0, 1, 2, 0. So we produce as much zeros as possible, and I think this is the best that we can do. We cannot modify this anymore, but your initial question, I did not understand it exactly, but this 1, 2, 0, you said that we did not change. We can change, but we can never make these zeros. And the change here would be because when we're playing with these other rows, these numbers are going to affect each other. Finally, this is the reduced row echelon form of the first question. When we did this first part, I asked you, I said, is this the reduced row echelon form? And you correctly answered by saying that no, this was not the reduced row echelon form. For reasons that we are trying to clarify them now. Let's separate them like this, with this red line, which gives the solution, first part of the solution and second part of the solution. Is it clear now?
Professor, I have a question.
Yes.
What if n and r were equal to each other? Does it mean dimension of the solution would be 0?
Yes, exactly. Yes, this is how it would be. When could this happen? Well, let me think for a moment. Let me think about this one. Let's repeat this again. You said when n is equal to r, then we'll say that the number of free variables, the number of equations, okay. Yes, we'll have no free variables, okay? If you have no free variable, that means that we have a unique solution. Yes, the dimension is 0, and the point, it has dimension of 0 by definition. This is a good question. So it looks like we learn now that a single point has dimension of 0. You extend this point, so imagine for a moment, let's do it like this. You have a point particle. Merë një kokër, që të thëmë? Një kokër grosh, një kokër... Që dimensioni ka ajo? The dimension is 0. Then you hit it, you put it on a plane, you hit it. What it's going to draw is going to draw a line, okay? It makes it one-dimensional. Then have another line, you make 2D and 3D and so on, but that's true. In this case, you have no free variable. The dimension of the solution is equal to 0. Dim is equal to 0. When is the dimension equal to 0? Here. So if you have a unique solution, then we say that the dimension of the solution is 0. Because it's on a line. Okay, is it clear?
Yes.
Okay. So if there are no free variables, the solution is going to represent a point.
Yes. But if we see examples, I hope things will become a little more clear.
Okay.
Okay. Yeah. Because let's think about this one for a moment. What ends up, imagine you have 5 unknowns with 5 equations. Okay. And let's think also for a moment. This is going to happen often when you have square matrices. You have here, how many unknowns do we have here? We have n unknowns, okay? And if you have a rank equal to A, that means that 5 unknowns with 5 equations, we can find a unique solution. But yeah, so far, I think we're going to cover this one a little more in detail in the future chapters when we do more about vector spaces, and hopefully we'll understand them a little better. Okay, would you like to give a short break?
So, Professor, just one more question.
Yes.
X3 variable because it has a solution?
Say it again, X3?
So we have two rows because the last row gives infinite solutions, right?
We have two rows here because we have an infinite number of solutions. Is it what you said?
No, because the row number 3 is 4 0, so it means that it has infinite numbers of solutions.
Yes. So let me say it like this. We have three unknowns, three equations. Apparently, we had two because one of them was the function of the other two. So the moment we have two equations, that means that one row is full of zeros, which then brings us the condition, not the condition, but the result that we have at least one free variable. The moment we have one free variable, how do the variables look like? They are like a constant s, where s can be a number in the real number space. And what is this s then? It's any number from minus infinity to plus infinity, which means that this is an infinite number of solutions by default. Okay. Is it more clear or?
Yeah. Okay.
Okay. We're going to see a couple of examples, not a few, at least much more. Okay, shall we give a short